Okay, good morning, everyone. This is Liang from Bosch Research, North America. Welcome to our session. So this is the eighth symposium on visualization in data science. Uh, this event is co-located in IEEE VDS and also ACM KDD. You may be curious how the VDS is co-located at both and VIS and KDD. Here are some like motivation and also our vision to shape VDS as a bridge to connect to community of VIS and KDD. So if you look at the whole technical spectrum of VDS, so from visualization community, we are seeking for advanced visualization and visual analytics tools to enable sophisticated data analysis tasks. On the other hand, we also need to leverage state-of-art tech research from statistics, applied science, machine learning, data mining. Actually, this has been a focus of the KTD community. So as a result, we are trying to bridge these two communities through VDIs and trying to bring researchers from both communities to explore open research questions and expecting more impact in various domains, including like business, biology, physics, humanities, social science, etc. So how did we get here? So here is like a little bit like, oh, the animation is broken. Bear with me. Uh, so the first VDS started in 2015 with the three VDS pioneers, then Daniel Kane, Hans Pister, and Claudia Silva, which is like founded back in 2015. And we have very successful 5 years till like 2020. That's the pandemic time. So it's quite challenging for everybody to get more paper and participation during this time. However, this offers an opportunity to think about how we can get more people in VDS. So because anyway, the other conference is also going on virtual. So that's where when we started the first VDS co-located at IEEE and also ASM KDD. So with the help of leadership of like Adam, Pierre, Alex from VASE, and Thorsten Mahler, and Claudia Plant from KDD. So this year, we still have like two sub committee from both VASE and KDD community. On this side, we have myself and other two pictures, Arvita Outley here in the front. And also we have Anna Christian from Tableau Research, she is joining online. So present our program for today. So this is our program for today. So we will have opening keynote from Dr. Daniel Fackett, and then we have 7 papers with a half-hour break in between, and then we will closing this event with a talk from Remex Chan. So before I introduce the first keynote, I would like to thank everyone, like the chairs from both KDD and this sub-community, and also the PC members, and all authors and the contributor and to make this happen. Thank you. Now I'm going to introduce our first keynote speaker, Jan Daniel Fackett. Maybe you can set it up while I introduce you. Okay, so Jan Daniel Fackett is a senior research scientist at in area and the head of research lab with at both. Let me just switch here. Okay, from University of Paris, Scala and INRIA. His research areas are visual analytics, information visualization, and human-computer interaction. He published more than 150 articles in international conferences and journals, include the most prestigious one in visualization like TVCG, Earways, Infoways, and also HCI conference like Kai West. He has been granted the IEEE VGTCG Visualization Career Award 2020, and also is a member of IEEE VGTC Visualization Academy, and also the ACM Siegel Kai Academy. He is a member of the Graphics Publication Board and AEF in chief of IEEE TVCG. Okay, without any further ado, I will just hand it over to Dr. Jin Daniel for this talk. Okay.
Excellent. You mind if I remove my mask for talking? Okay, I'll remove my mask for talking. I hope nobody objects. I'm far away from you. So, hi everyone. So it's a great pleasure for me to be here in person. It's been many years since I haven't seen many of you, and it's great to be able to interact face to face. So thanks for the introduction. And today I'll try to convince you that we need to do a step forward that is a bit tough technically, but we need to do it if we want to scale. So my takeaway message, I start with that. So if you are in a hurry and you need to leave, you know what I want to say, is that if you think about scalability in visualization and data science for exploration tasks, it will not come only from scaling up the infrastructure. Having bigger computer, bigger networks will not do it alone. And there is a reason for that, is that scaling the infrastructures and the resources will not solve the problem of latency. So if we want to solve that problem of latency for having exploration and interaction at human speed, we need to change programming paradigm. And right now, this new programming paradigm that I call progressive data analysis, but there are other names, I'll talk about it, seems to be appropriate. But then still, it's not catching up as fast as it should. And the reason is that it will need deep changes in our software infrastructure in order to be working on the whole pipeline. And this talk is about explaining you why and making this call for people, calls for action, for people to join and to devise the necessary mechanism in order for all the pipeline to work in a progressive way. So this is research work, but also development work. But my claim is without that, we will not be able to get to the next level of scalability that we need. Okay? So let me clarify what I'm talking about. So this idea of progressive data analysis has been there for many years, I would say. I'll go back to some of the history. But basically, what I want to do is I want to have a new kind of language where things are progressive. So the reason why I want that is that when you do interaction, when you want to interact with your data, you need to have a guarantee of maximum latency. And there are multiple setups, and there are, let's say, 3 levels of latency that are important, but the main point is you need to guarantee a maximum latency. Let's say 10 seconds for the sake of remembering. And so in the last 10 years, let's say, new languages have been introduced or new systems have been introduced that are a little bit different from what we used that we use right now. So currently when we call a function in computer science, and let's say that data science pipeline is basically a huge function. When we call a function, we call it once, and it returns an accurate result, as accurate as possible, in an unbounded amount of time. So when somebody gives you an API and say, call this function, you call it, you never know when it's coming back, but when it comes back, it has the right result or the best possible result. In a progressive setting, it doesn't work exactly the same. When you call a progressive function, it will return a series of results, not one result. And each result will be approximate, but improving over time. But each of the return value will be bounded in time. So if you say, give me a return value by 1 second, it will return a series of value every second at most, and the value will be improving with time. And so, in addition to that, a progressive function should return you something about how much is the progression, and what is the quality of the current return results. So if you need to know that in order to assess if it's good enough to make a decision. And the thing that is interesting with this idea of progressive data analysis of progressive function is that you're monitoring the result as a human or as a system, and you decide when the quality is good enough to stop the system and make a decision. The decision can be, this algorithm doesn't really work, so I stop it, or this decision can be, I have the answer to my question, I can stop the computation, I'm fine with the result, okay? So, in fact, you are trading time for quality. You decide when you stop, when you have enough quality. And what's interesting is that in the recent years, we've seen that you can compose progressive functions. So you can have the equivalent of a pipeline with some caveats. You can have loading, processing, visualization in a composed way. So that's what I will be talking about today, and I will try to explain to you why it's a good solution, but there are issues. So if you are not familiar with those progressive things, let's take a very simple example. One is a journalist at the New York Times asked his data scientist, give me the average age of Facebook users in US, Japan, Germany, and the UK. And I want that as quickly as possible. I'm writing an article, I want that. So the data scientist will connect to the Facebook API, call the Facebook API, which will return results for every user, one after the other. And he will connect a visualization, a progressive visualization, which will show the values for the average age of each of the user while the data is being loaded, and with a quality assessment. So here it's a progress bar. And at some point, the average age will stabilize. And so the confidence interval will shrink. And at some point, the data scientist will be able to answer the question with a level of confidence without waiting for the whole data set to be loaded and to have the exact value. So it will probably save time, save bandwidth, and give a quite accurate answer for the journalist. So that's one of the example of setting. It's a very simple one, and we have a paper on these kind of things later. Another one that we've been working on a few years ago was a similar setting, but more complicated, where you have a question, you want to see what were the tweets at some point about a topic. So here the topic is what has been discussed between Hillary Clinton and Bernie Sanders in the primary campaign, according to the tweets. So you start downloading the tweets. It will take time, and there will be thousands and thousands of tweets. And while you do that, the tweets are being downloaded. You compute sentiment analysis. You compute who are the main people tweeting. And then you show the projection and multidimensional projection of all the topics that are being discussed while the data is being loaded. So that's a progressive thing. And while the user is trying to see what's going on, the multidimensional projection of all the topics will evolve as it is monitored, and you will see new topics coming in, and the things will evolve. And on top of this multidimensional projection, it's a Disney projection here, you can have a k-means clustering that shows what are the main topics, and the user can dynamically decide to change k from 5 to 20 if the user wants more precision or want to track a particular question. So that's an example of a progressive system that helps people do their work quickly without having to wait a long time for loading, etc. Okay, so those are two examples, and I will maybe mention others along the presentation. So scalability versus latency. So there's been a lot of studies in HCI psychology and visualization that say that an interactive system should have a limited latency. And when an interactive system doesn't reach that, gets longer than that latency, it becomes unusable for exploration. So I think that's a very important message for people in the data sciences to keep in mind. if you have to wait 1 minute while you click on a button, the system is not interactive and your ability to do exploration is hampered. It's really bad. So that's not like, it would be better if it's not within those bounds, you cannot explore. The human brain is not equipped for that. But then the problem is that when you have more and more data, or the computation are more and more complex, when you start a computation, it will take more and more time. So the situation is that we have more and more data, more and more complex algorithms, and we want to be able to explore and to interact, but it will take more and more time, so we will at some point exceed the latency time. You cannot guarantee that you will do a deep learning training in 0.1 second, whatever the data, whatever the number of layers. So how can we maintain the low latency while managing more data and more complex algorithms? That's a key question. And if we don't succeed in that, for the visualization community, we might become irrelevant at some point. The database community will say we have terabytes, the machine learning community will say we have terabytes, and we say we can handle 10,000 points or 100 or 1 million points, and that's kind of irrelevant for them. So it's really a crucial question, I think. So then the next question is what is scalability? And we've been working on that question for a bit of time now. And what you need to remember on that question is that there is no accepted formal definition of what is scalability. We searched and we found a lot of partial definition, very specific, but there is even one person, Hill, who wrote in 1990 that he failed to find a useful, rigorous definition of scalability. So scalability has never been super well defined, but we can try to define it and in our domain and to find a definition. So we have a preprint right now with Gaël Richet, Daniel Reiskopf, Michael Sedelmeier, Alexis Pister, who's on the back, and Moataz. So to try to explain what is scalability in visualization. And so let me give you a small example. We start with this model of what is scalability. Scalability is based on 4 things: problem size, effort, resources, and assumptions. So problem size, you understand what it is. If I say I want to have more data, you want to have a larger number of data. But if you want to say I want to support more users, it's also a problem size, etc. That one is pretty easy. The effort is what you want to have in the end. So if you want to have a computation time, that's the effort you want to measure. If you say you want a low latency, that's what you want to measure. If you want to say FPS, frame per second, it's kind of related to latency. That's the effort you want to measure for the scalability. And then you have the resources, and the resources are, for example, all the things you cannot change easily: the number of cores you have, the amount of RAM you have, and whether you're relying on an external database and you're making some, you're using them as a resource. And finally, this last point I think is important because I'll use it a lot, is what are the assumptions you're making about the world around you when you're talking about scalability. And I will argue that in many papers that I'm reading about scalability, people are never very clear about the assumption they're making. So the assumptions are very wide. So they can be about the data, or the fact that the data is indexed in a database or it's not indexed in the database, that the data is loaded on the web or is present in the local SSD disk. But it can also be the fact that you assume that the user will do only task A and B and that's it. And for that, then you're talking about scalability, but then does it generalize? So the assumptions are super important to explain, and that's really a problem. So in what I will be talking about, the scalability will be in 3 different forms. So the first one is that latency should be under a threshold. So when I'm talking about scalability in visualization and I want to maintain latency at a particular level, it means I don't want to have a latency of less than 1 nanosecond. I don't care. I want the latency to remain under 0.1 or 1 or 10, okay? So this kind of meaning of scalability means I want all of my computation to be under some particular threshold. That's the same for video games. They want a particular threshold. Then performance is what people understand. I want to be able to be faster for problem size. And then there is this third thing, which is not always discussed in visualization. It's the quality of the result. Usually you get what you get in current systems. But when we are talking about approximate query processing or progressive system, you have the quality. And you want the quality to be as high as possible, but as high as possible for making a decision. You don't need a precision of 1 nanometer if you want to see if you're close to something or not close to something. So this thing of quality is also important, and scalability is related also to quality. So in a standard system, the latency is the computation time. You go to the end of the computation, you give back the control to the user. So the longer it takes, the longer the latency will become. So you don't have a control of that, and the quality is always as high as possible given the algorithm. Then you have approximate systems which are popular in the database. You say, I want to compute this, and I give you 1 second. And the system returns after 1 second, and it tells you, here is the approximate result, and I tell you this result is good in this confidence interval, plus or minus 10,000, whatever. And if you're happy with this confidence interval, you have the answer. If you're not happy, you have to do it again with a longer timeout until you are happy. And that's actually what progressive systems are doing automatically. They are starting and they're giving you a first approximation, and then they continue until you say, okay, I have the answer. So latency is controlled, the quality is monitored, and the compute type is decided by the user according to the quality, okay? So those are 3 different interpretations of scalability for different systems, but you see that the first one has a limitation. Latency is computation. So currently, how do people address the scalability problem? They just scale the infrastructure as they need. So in order to do that, you need to know what is the size of the data, what is the system you have, and then in advance, you do a lot of pre-computation. You have enough cores, enough memory, you load the data. You can do pre-computations, but you need to do that in advance. You can do workload prediction. Some people do that very well, but this can work or not. And you can do query approximation, as I was saying, but this can work or not. So that's the current way of addressing the problem, scaling the system, hoping it will be good enough. And if you know the data, you can scale it. So if you're in this particular setting, you're fine. If you know exactly what is your data, you're fine. You can do it. But here is my position. My position is that I see the situation of data science moving, and right now the web or the internet is our primary long-lasting data storage. All the data is on the internet. You may have some specific data locally, but you may want data that is on the internet. And in the internet, in between you and the data, there is a cascade of network and memory layers, okay? So you know that in your computer you have L1 memory, L2 memory, and you have RAM, SSD, etc. But then it grows and grows and grows up to the data on the internet. That's the current organization of the memory. And so currently, systems are not designed for working with this infrastructure of multiple layers. So currently what we do is we tinker with it, we download, etc. And my claim is that progressive data analysis will allow taking into account the viscosity of this whole infrastructure for doing data analysis at scale. So this viscosity is very important. Everything takes time, lags, etc., etc. So it has to be taken into account. And maybe you have in mind, okay, but why do we need that? And I think this is the difference between cold-started exploration and prepared exploration. So most of the people doing scalability are assuming you do a prepared exploration. So you know exactly what you want to analyze. You will do it a lot of time. And then you download everything in advance. You do the indexing. You do pre-computation. You have everything ready, and then you do the exploration at the speed that you want. You have guarantees. But then the time to get the data, clean it up, prepare it, doing the infrastructure scaling is not taken into account for the exploration time. It's kind of removed from the whole time. If you do one-shot exploration, everything should be taken into account. You download the data, you have to discover what is in the data, you have to know what you will get, what you will keep or not, transform, wrangle, etc., up to the visualization. So everything is part of the exploration, and this is part of the time. And so, of course, that's not what we do right now. So in the audience, I'm pretty sure people will say, who needs to cold start this exploration? We don't do it. Is it really necessary? And then I'm an old man now, so I'm going back to the 90s. And when the web started, people say, why do I need the web? I want to see a document, I use FTP. I go to the website where the document is, I download with FTP my document, and then I use Word or WordPress in order to look it good enough. I don't need the web. But then when the web started, everybody used it because nobody is doing FTP, download the document, search it, whatever. So the web is actually a simple way of accessing document that really lowers the barrier by providing a very simple infrastructure that is completely web compliant. And by the way, the load has progressive loading, progressive layout, progressive image rendering since 1992. Okay, so progressive is not totally new in the world. So what I want to do, and I think what we need to be going to, is to be able to have this cold starting of data exploration at web scale, and with progressive data analysis in particular, all right? So just to make it fast, I'll give some history of this topic of progressive data exploration. So some people think it started from the database community and Joe Hellerstein creating this, what he called online aggregation. You do a simple SQL query that computes an average, and instead of waiting for the average to be computed, you show this bottom left thing that shows the current average and then the confidence interval, and then it goes on. It has 14% loaded so far, and it goes to the end, and at the end it gives you the real truth, but if you're happy at any time, you can stop it and you have the answer. So Hellerstein did it in 1997, and it's still a topic in the database community. But it turned out we have been using progressive visualization not since '84. I asked Peter Eads, he didn't know when was the exact time when people started to show the graph layout for force-directed graph layout interactively, but let's say around the 90s, started to work. So we are familiar with those graph visualization that do the layout dynamically, interactively, and we are familiar with that. One thing we must remember is that the implementation of these things are usually a bit complicated. Now with D3 it's becoming a bit simpler, but it doesn't really scale to large sizes. But having an efficient implementation is not that easy. And then later in 2004, Tamara Munzner and Williams presented this idea of progressive multidimensional projection. So multidimensional projection is also an iterative algorithms for computing those maps, but they take a lot of time. And so their algorithm is showing the development of the algorithm, but the user can say, I'm more interested by this particular area, so put more effort in this particular area. So that's what we call the steering aspect. We can interact, and we can even interact with the algorithm to tell the algorithm what is our interest. So, okay. In 2014, Stolper and Per and colleagues published this book where they coined the term progressive visual analytics. And they explained that instead of waiting for the algorithm to give you the answer and then showing the result, you can basically run the algorithm and get the results and explore them before it's all done. So they also give a list of very interesting requirements for progressive system to be usable. I will not go into detail here. And what's interesting too is that they use it for pattern mining. So in pattern mining, it's not about computing one value and having an approximate solution. It's about having multiple results that are as relevant as possible. So it's not about accuracy, it's about relevance, but it works about the same. It's a question of quality. And then there has been a lot of work. I'm just coining my own, but with Jamie and Joe. But the point is that we've been creating algorithms and data structure that are progressive in nature. So here, with this paper, we show we can create, we can manage a k nearest neighbor data structure progressively while we load data. It keeps on updating. But more interestingly, we show that it can be connected to a pipeline. So after the k nearest neighbor, which is not a goal, you can connect it to a regression and then visualization, or to density estimation, like on the bottom, or even to a t-SNE algorithm and then the visualization. So you can combine progressive algorithms and system and they remain progressive. And it also introduced an interesting problem, but I'm not going to talk about it too much, about the fact that you need to involve the user, because at some point the user is asked whether if he redisplay or if he restart somehow the algorithm, he will increase the accuracy, but it will break the stability. So you need to provide a way for users to decide keep the stability or break it and keep the accuracy. And that's an interesting question to address, also a research question. And then we also did with Kartik Badam and Niklas Enquist some work on what is needed for the user interface in order to support progressive data analysis, because then all of those modules need to provide some feedback control, and that's not standard. So we explain what are the requirements and why it's a requirement and how to do it well. And then to finish, there are also questions that you may wonder, like, okay, you have technical results, but are humans able to cope with progressive systems? Can they deal with it? And the answer seems to be yes. So first, there's been an experiment that we did in 2007 with Emmanuel Dragon and colleagues that shows that if you have a system that is blocking, okay, if it's not non-blocking, it's easy, you interact with it. If it's blocking, even for a small amount of time, the exploration is hampered. It's really bad. People are basically forgotten their question by the time they receive the answer. But if you use a progressive system, it's as good as an immediate system. So progressive seems to be good for exploration. And then the next question is, can people make early decision with a progressive system without making mistakes? So if I tell you, you have quality on one side and time on the other side, but you can stop before the end if you have a good quality enough, it's kind of a tough problem. And then we will show, this Thursday we have a presentation here, that actually people, for some cases at least, but that's promising, can do this decision to say, I'm stopping here because I have a good quality enough, and that's right, it's a good quality. So in summary, yes, humans can use progressive systems, it seems, at least. And there's been progressive databases that has been experimented, progressive visualizations, several progressive algorithms that are now can be combined. Great, so let's do it. But then the problem is that they do not interoperate at all. So currently, if you have a standard pipeline and you have a better algorithm, you just replace the old algorithm with a new algorithm because they all use the same data structure and APIs. It's very easy. It's just like you have the pipeline, remove one, put another one at the same place. For progressive, we are not even at this stage. We don't know how to communicate between a data management, a database, and a progressive system. We don't know what is the input of a progressive machine learning system and what is the input of a progressive machine learning. We don't know how the system will react when something changes unexpectedly. So we're at this kind of stage where we know it's possible, but it will take some technical steps in order to work. And that's why I'm calling for an action on that. I think if we want to see machine learning and visualization used at scale, we need to work on this next technical problem, which is to make sure that all of these systems can interoperate so we can connect them together. So right now, when I'm doing a visualization that is progressive, I cannot use a scalable database from my colleagues because it just doesn't connect to my system. And I don't want to do one because I'm not a database person, so it will be very bad and I will waste a lot of time. So really, PDA will remain interesting, but data exploration will not scale if we don't solve that technical problem. So coming back, if you stayed that long to the conclusion, scalability is possible, but it will not rely only on scaling the resources. We need a new paradigm. Maybe there will be another one. I'd be happy if there is another one. So progressive data analysis is a promising solution, but it will require now to make sure that everything interoperates, because otherwise it will not work. And I have a lot of things to say about it. The domain of online aggregation hasn't really caught up in the database community because there was no use case, because there was no progressive visualization after the database. So how can you sell a progressive database when there is nothing to use it in the end? It's not a very good selling point. So if you're interested in working in this domain from companies or from research domain, but you want to be able to do exploration at scale with machine learning, simulation, etc. I think it's contact me and I'll do my best to create a working group and do something so we can really have this progressive data analysis at scale working in our community and reach scalability. Thank you.
Thank you. Thank you. Do you have any questions from audience here and also questions online? I checked online. We don't have a question online, but here.
Very interesting talk, thank you. You said some programming languages don't support regressive data structures. Why is that and what is missing?
I mean, what I meant was more that the standard data structure are clearly not meant for progressive use. And even if you think about like Python right now used for data analysis, if you're loading a file in a progressive way in Python and you're using Python pandas, which is the standard, growing a Python pandas data frame is just hell. It breaks. It just breaks. So all of these systems don't sustain the assumption that of progressive systems. They break everywhere. So that's what I meant actually.
We still have a time for.
Thank you, Jean-Daniel. I wonder, how do you see the relationship to some early work that came more from the Cybis community, like LDAF next door? Keywords would be in situ or computational steering. How do you see that this could be linked, or where do you see the differences?
So in situ is slightly different. I have a list of things that people compare progressive to, and in situ is one. In situ is driven by the algorithm, right? You have one algorithm that is running and you want to have a monitoring mechanism and some control mechanism. So it's slightly different, but it's somehow related. And clearly in the last 10, 15 years, the Cybis community has been doing a lot of work to create infrastructure to support in situ visualization and control. So the work that I'm calling for general visualization has been done in the Cybis community. So there are some Cybis algorithms, for example, for topological data analysis that are progressive for sure. But again, when you talk about Julien Tierney, I don't know if he's here, he will tell you that he wanted to have the visualization being progressive and it just doesn't work for now. So my feeling is that it's related, but it's quite different too. So it's more a topic of confusion than a topic of unification, I would say. Okay. Great.
Thank you again.
Thanks. And you can find me during the whole week, so don't hesitate.
Okay, thanks again, John Daniel, for such an amazing talk. My name is Alvita Otley, and I'm one of the paper chairs, and I'm delighted to present our Best Paper Award. A quick note about our Best Paper Award and about this paper specifically. So as Liang mentioned earlier, VDS was at both KDD and Viz this year. And what made this specific paper stand out is it got excellent reviews both from our KDD reviewers as well as our Viz reviewers. So this paper does a really good job as bridging the two communities, and I'm really excited to present our Best Paper Award goes to Pseudo Interactive Pattern Search in Multivariate Time Series with Locality Sensitive Hashing and Relevance Feedback. And this will be presented by UConn. Another thing I forgot to mention is that our Best Paper Award also goes to TVCG. So this was a really great paper and very well deserving. So let's welcome Yukon, who's going to be presenting virtually right now.
A ubiquitous task. For example, there are various sensors in a car, and they record numerous events. Their measurement forms a multivariate or high-dimensional time series because there are multiple checks in the data. Our engineers search for an indicating signal to find the best timing for their engine control algorithm. They search for gear change events to study the traction loss during these events, and they search for certain periods when some engine cylinders are deactivated or reactivated to study the vibration during this period. No problem. Then I will open the live session and wait for the Q&A session.
Sorry, on our end, they just switched the broadcast to the Zoom video. So we're just gonna.
So I need to share my screen again, right?
Yeah.
Okay. Sure. So could you see my screen now?
Yep.
Yeah. And please tell me when I should start.
You can go ahead and start. Thank you.
Now? Okay. Hello, everyone. Our topic is multivariate time series retrieval. Well, it is a very ubiquitous task. For example, there are various sensors in a car, and they record numerous events. These measurements form a multivariate or high-dimensional time series because there are multiple checks in the data. Our engineers search for an indicating signal to find the best timing for their engine control algorithm. They search for gear change events to study the traction loss during these periods. And they search for certain periods when some engine cylinders are deactivated or reactivated to study the vibration during this period. These tasks are all backed up by multivariate time series retrieval. This task can be challenging. Our engineers search for events in measurements spontaneously. That means there are no labels and they wish a prompt answer. So supervised deep learning won't work. Sometimes our engineers can only narrow this problem down to maybe 10 to 20 checks, and they would like to know which checks are more important. For example, they want to study or analyze the error routes. Moreover, the notion of similarity itself is subjective and task-dependent. As a paper in 2016 by Correll says, no single algorithm accounts for human judgments of time series similarity. So, we pose the research question: how to assist users during spontaneous pattern search in high-dimensional time series regarding subjective similarity efficiently. In accordance, our major contribution is the extension of maybe the fastest algorithm on the world, namely hashing algorithm, with relevance feedback to meet the challenges. So we try to combine automatic multivariate time series retrieval with relevance feedback. For one thing, we have a publication this year. It deals with various distortions in time series retrieval, especially intercheck distortions. However, it is not very scalable for very high-dimensional time series. For another, we found a very interesting work based on locality-sensitive hashing with excellent scalability with respect to data dimensions. We chose it as our baseline. On the other hand, relevance feedback for time series traces back to this paper in 1998. Recently, An excellent tool, Peaks, is proposed. However, it takes several days with Top Gears to train a deep learning model. This is reasonable for their relatively stable epigenomics use case, but not very suitable for our spontaneous use cases. Moreover, it is not really designed for very high-dimensional time series. So we try to combine the best of the two worlds and propose relevance feedback-driven, locality-sensitive hashing-based multivariate time series retrieval. But wait, what is locality-sensitive hashing? Why do we go for it? Well, the general hashing aims for the exact same thing. If you download a big file, you would like to check its hash value and you would like to know if the file is changed, even for the smallest possible changes. In contrast, LSH aims for similar but not necessarily the same thing. This property makes it very suitable for pattern search. In pattern search, you would like to find similar patterns but not necessarily the exact same patterns. Okay, so how does LSH work? Conceptually, it starts with data points in a high-dimensional space. It initializes random hyperplanes, and these hyperplanes cut the data space in multiple subspaces. If two data points are in the same subspace, they are potentially similar, and the result is recorded in a hash table. However, the random hyperplanes are random, so it's likely that two close data points are separated. Therefore, we need multiple sets of hyperplanes to avoid false negatives. That's the general concept of LSH. We derive our method from the if-dive circle. It extends automatic data mining algorithms iteratively with 3 more steps, namely sampling from the result, inviting users to provide feedback to samples, and updating the model based on user feedback. Now, in our case, we have multivariate time series. We have a query. LSH merges the checks and filters out the majority of the time series windows, and then we draw samples and invite the users to label the samples as correct, incorrect, or indecisively, typically 5 to 10 labels per feedback round, 3 to 5 rounds, and then we update the hash model. So our baseline is an established LSH algorithm for time series. But that's not our contribution. We extend this established method with a user feedback loop. We assume that the randomly initialized hash functions are trainable. Okay, so we have output from LSH. They are ranked by a distance measure like dynamic time warping. And so we get a similarity distribution of the time series windows. They survived LSH. Then we draw samples from this distribution, and we invite the users to label them. Unfortunately, we can't make very good use of the negative labels, so we collect the positive labels. We calculate the variance of each check in the positively labeled samples. If the variance is low, it indicates that this check is important. Based on this intuition, we can update the check weights. They are kind of feature importance. With that, we can modify the hash functions in the LSH model. We have implemented a prototypical UI to support this algorithm and encourage readers to watch the video mentioned in the paper. We have evaluated pseudo in 4 threads. Besides accuracy and speed, we have conducted a scalability test to examine the relevance feedback mechanism, and we have conducted a use study with an expert. We found that pseudo surpasses other methods in terms of speed when they are say more than 5 checks in our example. Relevance feedback not only improves the accuracy, but also selects or attaches more weight to important checks or important features. In conclusion, we propose pseudo, an efficient, adaptive, and interpretable tool for visual pattern retrieval in high-dimensional time series based on locality-sensitive hashing and relevance feedback. In the future, we plan to better our query definition interface. We want to examine scalable visualizations for high-dimensional time series, and we would like to make good use of the negative labels. Thank you very much for your attention, and be very glad to answer your questions.
All right. Thank you for
Hello.
that great
Oh.
presentation. You can keep sharing your screen. We are
yeah.
still broadcasting. Yeah.
Okay.
So we have one question coming in on the Slido, which is, can you envision this method being applied to video sequence data? And what are the potential limitations?
Okay. So, a different kind of data, I think it's well possible. I suppose that it's also possible to use hashing to, say, simplify the video data, and the problem is how can we update the hash functions accordingly. In my opinion, it could be possible, but we need to, say, dig into the details of the algorithm to really find a way to tune the parameters, or tune the parameters in the hash functions. Of course, there are some limitations in the method. In my personal opinion, this method, at least our method, is still linear, so it has hard time to capture, let's say, non-linearity, non-linear patterns. Well, I think that's the major drawback of our method, but I think we can work on it to improve the method.
Awesome. Thank you for that answer.
Thank you very much.
Okay. We are going to move on to the next presentation for just to keep track of time now. So the next talk that we have is by Aaron Chamak, and he's going to be speaking about motif-based visual analysis of dynamic networks. We're going to see whether the tech chairs play the video or whether Aaron is going to present. Okay. Aaron, why don't you go ahead and present? It looks like, oh, okay. Yeah, they are playing your video. We're good.
Identifying similar and dissimilar network structures over time. First of all, let us start with a brief recap of motifs. Motifs are small induced subnetworks that can be seen as the basic building blocks of a network. In network visualization, motifs are often used to abstract and simplify common subnetwork structures. For example, Dohn and Schneiderman display and abstract motifs as complex glyphs to reveal hidden relationships in large networks. However, there is still relatively limited research on how motif-based visualization approaches can be used for dynamic networks. Which brings us to a research question: how can we provide a scalable overview of significant changes in subnetwork structures in dynamic networks? In our paper, we compare a selection of related work to delineate our work and highlight the research gap we intend to close. To summarize the results of this comparison, up to this day, visualization approaches refrained from using motifs to display dynamic networks, although such motifs can provide useful, scalable overviews of evolving subnetwork structures. In this work, we therefore propose two pixel-based visualizations to provide a scalable overview of evolving subnetwork structures in large-scale dynamic networks. Our main goal is to view structural changes, temporal states, trends, and outliers. The first pixel visualization is the network-level census view, which depicts an entire dynamic network. The main idea is to compute and explore significantly occurring network motifs over time. In the first step, we compute network censuses, also known as the motive significance profiles, which are useful for studying similarities between networks. Network censuses capture the significantly occurring motifs compared to the expected occurrences in a random network. Positive values indicate that the motif is significantly overrepresented, and inversely, negative values define an underrepresented anti-motif. In the second step, we sequentially order and visually encode each network census as colored pixel bars, creating a dense pixel-based visualization. Overall, the basic idea is to compute and display significantly occurring motifs as compact and clutter-free pixel visualizations. Second, we propose a node-level subnetwork metric view, which allows comparing multiple networks in more detail using graphlets instead of using motif-significant profiles. The main difference from the previously network-level census visualization is that we obtain one pixel visualization for a single network, since we compute graphlet vectors for each node. The node-level pixel visualizations are useful for comparing the structural neighborhood of nodes within and across several networks. Graphlets count the instances of induced motifs occurring in the n-hop neighborhood around a given node. Graphlets for 2 to 5 nodes around a particular node are also known as the 73-dimensional graphlet degree vector. Comparing two graphlet degree vectors enables us to compare the local topological neighborhood of two nodes. For the second pixel visualization, we basically compute graphlet degree vectors for each node and afterwards display the vectors again as pixel bars to create a dense pixel-based visualization. The main difference here is again that we obtain one view for a single network as the graphlet degree vectors are computed for each node. We also want to emphasize that two graphlet-based pixel-based visualizations of two different size networks will also have varying lengths. In addition, we propose several reordering strategies to reveal similar pixel bars in both pixel-based visualizations for the X and Y axis. The reordering strategies help investigate changes in the underlying evolving subnetwork structures and orderings, and thus influence the visible patterns in both pixel visualizations. For instance, through reordering and clustering the motif significance profiles, we can uncover similar network superfamilies in the dynamic network. Moreover, we cluster the vectors and allow users to expand specific clusters to analyze them in more detail if the x-axis does not scale with the number of time points or nodes. So let's talk about how we can interpret the patterns in both pixel visualizations. Users must identify similar and dissimilar pixel bars in both pixel visualizations to detect relevant visual patterns. Overall, discovering such similar pixel bars is relatively simple due to the Gestalt principles of continuity, similarity, proximity, and closure. Please refer to our paper for a more detailed description of potential visual patterns and their interpretations. Next, we will shortly introduce our prototype. The toolbar enables displaying various real-world dynamic networks and arranging the pixel visualizations with different reordering strategies. The network-level census view displays the motif significance profiles of each time step. In this case, a column represents a day in the Reddit social network dataset. The view can be explored through zooming and panning, and the values can be examined via a mouse-over tooltip. The network view displays the underlying network structure as a node link diagram. The selection of a pixel bar adds a node-level subnetwork metric pixel visualization. Users can select multiple days and compare networks using the graphlet degree vectors. The views are all linked and each can be explored via zooming and panning. In both pixel visualizations, various patterns may remain hidden and difficult to detect due to the sheer amount of visualized data. Hence, we propose reordering strategies. The rows, meaning the y-axis, can be reordered based on several statistical heuristics. For example, the y-axis can be sorted by the mean or variance value of each presented dimension. As for the temporal dimension, the x-axis, we propose multiple reordering strategies. For instance, we cluster the network censuses and allow users to expand and collapse specific clusters. This increases the visual scalability of our pixel visualization. Moreover, the y-axis can be sorted based on network metrics such as the network transitivity or the page rank of a node. Overall, the use of such rearrangement strategies for both axes helps to identify patterns that might otherwise remain hidden. Next, we shortly discuss the three dynamic networks described in our use cases. First, the Facebook data displays wall posts between users in the city of New Orleans. We can easily identify significant structural change in May 2006, where some triads start to be more frequently overrepresented due to an increasing number of Facebook users. Second, the Bitcoin data presents a Who Trusts Who network on the Bitcoin OTC platform. In the data, we can easily spot two trends in which the 8th triad is strongly overrepresented. In the period, there was an increased trading activity. We can also apply different reordering strategies to group similar temporal states and trends together. The third dataset is the evolving social network Reddit dataset, which encodes hyperlinks, edges between subreddits nodes. We apply different reordering strategies to help identify an outlier period, such as in the beginning of 2017. We investigate the visible outlier period by displaying in two node-level metric views. To increase the network view scalability, we cluster networks with more than 100 nodes and afterwards display each identified cluster as a node link diagram. Afterward, we cluster and interpret the node-level metric views to expose structural similarities and differences between two networks. The investigation of the detailed view reveals numerous hyperlinks between subreddits dealing with the National Football League (NFL) in the USA. Overall, the use cases highlight how both pixel-based visualizations can be used to identify structural changes, temporal states, trends, and outliers in a dynamic network. Our approach has also some limitations. The first step in the pipeline depends on the selected motifs and the used null model to compute the network censuses. Hence, these two parameters have to be set by a user as they depend on the application domain and the user task at hand. Moreover, discovering large motifs is computationally expensive. Therefore, computing motif censuses is only feasible up to 8 node motifs. In addition, we also identified the risk that white-colored pixels might be misunderstood. The white pixels do not necessarily imply that the motifs are not occurring in the network, but rather that they are not occurring significantly more or less often than expected in the null model. Furthermore, both pixel visualizations remain challenging to read due to the sheer amount of displayed data. We address this limitation by providing various reordering strategies to highlight similar rows and columns. In future work, we plan to also investigate new reordering strategies for the comparison of multiple subnetwork metric views. Scalability of our approach poses another challenge since the subgraph matching problem is known to be NP-complete. Therefore, we suggest pre-computing the network censuses. We also increase the visual scalability by aggregating and simplifying clusters of similar pixel bars. To sum it up, we presented two pixel-based visualizations based on network censuses and graph degree vectors to provide a scalable overview of structural changes in large-scale dynamic networks. The pixel-based visualizations reveal similar temporal states, trends, and outliers in dynamic networks using motifs and node-level statistics. Moreover, we also proposed reordering strategies and interpretations of the potential visual patterns in both pixel visualizations. The code for the prototype implementation is available online, and with that, I want to thank all of my co-authors and the reviewers for their extensive feedback.
All right, thank you for that. Aaron, we have 2 questions for you. First one from Cameron Yick. How do you decide which motifs to include as rows in the network level census? And what questions would you ask to decide whether a motif was helpful or not?
So the motifs that we include currently or as default are the triads. There are 13 different triad motifs available, but the selection of the motifs basically depends on the application domain. For instance, in biology, feed-forward loops are interesting, so including pods with feed-forward loops could be interesting for the investigation. And so basically, this is user task and application dependent, application domain dependent. And the second part, what question would you ask to decide whether a motif was helpful or not? Depends on also the representation. So if the motif is occurring as expected as it would have been in a random null model, so if I just have a white row with just white pixels, then it's usually not really useful to analyze that motif.
Cool. We have time for just one more quick question. This comes from an anonymous question poser. So it seems that the focus is mainly on the pixel-based view. What do the experts say about the network view? How much of it was helpful for their analysis? Can you tell like one simple exchange where both that were mandatory for the analysis?
So the network view itself is then useful if you want to like both pixel visualizations give you an overview. They are compact, but at the end, still, people usually want to also see the network structure to see how the structure is looking and investigate the network in detail. And in the case of the data sets and the people that used and analyzed our data sets, we had the problem that we have these huge networks, and sometimes people were overwhelmed with also the network view. So that's why we also try to simplify that. But in the case of the network analysis itself, I think the pixel visualizations help to find interesting moments in the dynamic network and also interesting local neighborhoods for the node level subnetwork view. But at the end, people always want to see the network structure and investigate or explore that in detail. So.
Awesome. Thank you very much. We're going to move on to our next presentation now, which is from Rock here in Penn. And he's going to be talking about how data scientists communicate intermediate results, and he will be presenting live. So take it away, Rock. Rock, when you're ready, can you also unmute yourself and share your video, please?
Can you see my screen?
Yep, you're great. Go ahead.
Hello, everyone. Today I'll presenting our work, how do data science workers communicate intermediate results? Oftentimes, when we think of data science communication, we think of how we communicate our final results to the lay audience. We might think of reports or highly polished visualization like the ones we see here. And in the past, most studies have focused on this facet of communication in order to develop tools for data scientists to share their findings with others. However, we have very little formalized knowledge of how data science workers communicate within their teams before delivering this final output. This intermediate stage in the data science process is arguably just as important as sharing final results. So in this work, we argue that intermediate communication should be a distinct collaboration element as it allows team members to collaboratively create that final product. Since the goals of intermediate communication have differences from that of the final communication, understanding this communication process is an important area of work that has the potential to inform the tooling design to help data science workers collaborate with each other in the future. So in our work, we contribute a more nuanced understanding of the intermediate communication process. In particular, we identify 4 major factors influencing this process. Spoiler alert, in this presentation, you will probably hear a lot of familiar incidents as data scientists yourselves. So to answer our question, we interviewed 8 self-identified data science workers. We guided our interview with the following questions: who, why, what forms, and what challenges do the data science workers have? So based on our interview analysis, we were able to characterize the communication process with 4 factors. So communication goals, shared artifacts, a communication mode, and the audience. First, let's talk about the communication goals. In other words, what might have been the reasons that workers want to communicate with the team members instead of completing the work by themselves. So here we have 8 goals. Each goal highlight a different type of information that needs to be exchanged from that communication. For example, if the goal is reporting progress, then the most important information to be communicated would be the work that has been done, such as the statistics related table and charts, versus if the goal is understanding legacy code, the most important information to communicate is how to use and run that code. And we also observe that different goals for communication influence how teams are communicating in terms of the frequency, the artifacts, and the channel and the audience. Now let's talk about the shared artifacts. The type of artifacts being shared has an effect on the type of communication taking place. First, I want to talk about the documentation, which may consist of, for example, Google Docs, READMEs, comments. These are important for communicating the experimental setup, the results, and the project architecture overall. And input data for analysis or modeling. So workers typically communicate with each other about where to find data, its schema, and how the data should be stored. And code or scripts, workers might communicate about their scripts do, they might debug their code and collectively write their code. Finally, figures and tables. This perhaps is the most related to what we traditionally thought of as communication to the audience. But one noticeable difference is that most of the visualization here are pretty much just static. So it might be worth exploring design opportunities to automatically turn static plots to interactive one based on the user behavior history. Now the next stage, let's talk about the communication mode. So whether the communication is taking place synchronous or asynchronously. So in asynchronous meeting, data science workers communicate via, for example, Slack, emails, and documentation. It often involves synthesized write-up. It allows the workers to spend a long time thinking about what they will say and gives them time to generate new shared artifacts. However, some participants find it hard to provide necessary information to have an in-depth conversation in an asynchronous setting. It's also easy to just get blocked while waiting for somebody with no response. In contrast, in synchronous communication, data science workers are communicating via, for example, meetings, phone calls, Zoom meetings, Discord. It might involve screen sharing and can facilitate a good environment for brainstorming, debugging, or getting feedback, since communication can happen very quickly and there is less pressure to be concise. However, it also presents challenges within the pressure of peer programming and the difficulty to give feedback on the fly. For instance, one of our participants mentioned that when you're just on the spot, it's often hard to come up with a good answer. And most participants use both modes of communication and often move back and forth between the two. Last but not the least, let's talk about audience. We found that the audience affect how they will present intermediate results. So if a data science worker is talking to someone working under them, they might take on a mentorship role when they communicate tasks and explain data science method. So we characterize this as a top-down communication. So in bottom-up communication, which is the reverse relationship, if the workers are talking to someone above them, such as the managers or advisors, they will want to show the project in a way that encourages continuous support from the higher up in a concise way. This typically involves polished and concise presentation that may involve emphasizing positive results, or only show the positive results or challenges, negative results or challenges when there is an incentive to do so, such as getting more time, resources, or funding. So if they are communicating with a peer, the data scientist is typically very frank about the challenges they are encountering, so they can receive honest feedback. Just recall the last time you code with your colleagues. So another type of audience involves the technical expertise. So if the audience doesn't have the technical expertise, the data science worker might synthesize information in a way so it will be understandable by the audience. Several of our participants noted that non-technical audience, which typically on the higher up, tend to think that, for example, the ML is like magic, and they only cared about the result, not the details of how they were generated. And now we have gone through the characterization. A key takeaway is that the intermediate communication is a complex process and has many design opportunities. So an immediate question that we want to ask is that, what's going to be the next step? So future work could further leverage our findings or structure to build a more comprehensive framework that shows how various shared artifacts are used that can guide the design of intermediate communication system ultimately. To elaborate, our work surfaced the 4 unique factors and showed anecdotal evidence of the interplay between different factors. But future work needs to more systematically or quantitatively examine how artifacts are being used for different goals, modes, and audience. So we'll pay attention specifically to artifacts because it's unique in the data science communication compared to other general purpose communication, such as imagine chatting with your colleagues or a product development team. With such framework as future work, we can potentially augment the existing general purpose communication tools to tailor specifically for data science work, which surrounds with unique data science shared artifacts. Something that might have a great interest to VDS audience is to incorporate the existing visualization tool in such a intermediate communication system. Thank you so much. For more detail, please look at our paper or contact us directly via social media or in person.
That's great. Thank you for that excellent talk, Rock. I have a question for you as other questions are coming in. When you look at these communication processes, do you notice any sort of breakdowns, between what you identified and how that affects how smoothly the communication goes, and whether there are opportunities to develop tools when those breakdowns occur?
So by breakdown, do you mean like there are like distinct difference between the kind of communication mode or type of communication?
Yeah, sure. So it's like as a data scientist, I might want to communicate something in a certain communication mode to a stakeholder. It doesn't work. They lose the information. The artifact isn't effective, or something like that. Did you observe these kinds of things, and how do you think that affects the tools that we develop for those kinds of situations?
Yeah, that's a great question. So remember I talked about the different goals for communication, right? So in the earlier stages of the data science project, you can think most of the communication surrounds around the like higher level topic. So very little, I guess, discussion around coding. So I think there's got to be the tooling got to support a higher level discussion on the literature instead of the like detailed like what we traditionally think of like collaborative like coding environment. But on the later stage, as you progress, it's good to keep track of the linkage between the codings in the later stage and the broader pictures, because you always change ideas. You can try this kind of bigger ideas. It would be nice to link kind of the general ideas to a specific implementation, and kind of keep the provenance of that, that analysis track. That's kind of a thought I had when you asked me about the specific breakdown, because I saw, there's a very apparent breakdown between the early and later stages of the pipeline. Does that make sense?
Yeah, awesome. Thank you very much. We're going to move on to our final talk of this session. Just as a heads up, we're running about 5 minutes behind as we resolve some of the new technical things. But we're going to have Agapi Risak, who's going to be playing her video. And she's going to be talking to us about Biascape, visual unfairness diagnosis for graph embeddings.
Biascope, a tool for visual unfairness diagnosis in graph embeddings. This is joint work with Bruno Scarone, David Liu, Aditya Pandey, Brennan Klein, Tina Elias-Irad, and Michelle Borkin from Northeastern University. As machine learning systems affect more and more our lives, algorithmic fairness in this context has become an important topic for both researchers and practitioners. In our work, we focus on graph embeddings. That is a machine learning model that maps every node in a graph to a vector in a metric space. You see here a 2D projection of an embedding. These embeddings are used for different machine learning tasks that can be human-centered. Think about friendship recommendations to social media or targeted advertising. But what about bias or fairness in this case? There are many ways to quantify bias that have been proposed in the literature for graph embeddings. They are usually in the form of fairness scores for nodes or graphs. These scores are useful, but the number is not enough to gain insight into what is causing the measured bias, what are the contributing factors. It is important to have transparency on how the scores are computed. To achieve this, we propose to employ visual methods that support visual unfairness diagnosis for graph embeddings. So this was our goal in a collaborative effort with domain experts from the graph mining community. There are certain important aspects we identified that guided our design. First, as we saw, graph embeddings can be part of multiple machine learning pipelines with end products that affect human lives, but it is important to detect bias early in the development process. Previous works have focused on visualizing unfairness in the end task. Instead, we focus on the earlier stage, understanding bias in the embedding itself, irrespective of the task. That way, we design a tool that would be helpful for researchers to evaluate the embeddings they create, and also for practitioners that aim to use these embeddings in real-world applications. Another important aspect is that it is hard to define fairness. Many notions have been proposed, which are in two distinct categories: individual fairness and group fairness. Individual fairness aims for all individuals to be treated similarly, which aligns with the concept of equality. On the other hand, for group fairness, all groups should have similar outcomes, and this way we can detect bias against minorities or disadvantaged groups. In the first figure, individuals are treated similarly, irrespective of their differences. In contrast, in the second figure, we have three different groups, and the focus is to guarantee an equal outcome for all. Through an iterative collaborative process, we identified three main tasks that together support visual unfairness diagnosis for graph embeddings. First is the statistical summary of the graph, where the user gets statistical information about the graph that may be useful for understanding unfairness. Next is the embedding comparison with respect to fairness, where two embeddings of the same network are compared so that the user can identify which embedding displays the most unfairness and where in the graph the unfairness is concentrated. And finally, the unfairness diagnosis, where the user understands why a node is unfairly embedded and which are the exact factors contributed to the measured unfairness. The three tasks together synthesize a full unfairness diagnosis workflow with two stages. First, the overview, which is a high-level understanding of unfairness, assisted by statistics and comparison. And second, the drill-down stage, which corresponds to gaining insights into the reasons and motives that cause bias. With all this in mind, we developed our tool, Bioscope. The tool consists of three views, together supporting our three main tasks. Let's walk through its components. So first, we have the statistical summary view. For the Facebook network here, we can see some statistics and the degree distribution bar chart. Next, we have the unfairness comparison view, a side-by-side view where the user selects two embeddings of the same graph to compare. The statistical summary and the comparison views together form the overview, which is the first stage of our workflow that we previously discussed. Next, the unfairness diagnostics view, which is again a side-by-side view of the local graph topology and the corresponding embedding subspace. This view supports the latter stage of our workflow, that is the drill-down stage. Let's see some more details now. Let's see here the comparison view. The user selects two embeddings of the same graph to compare. The unfairness scores for each node are encoded via color, where the darker is associated to more unfair. We display the graph with the same layout side by side to help with effective comparison. For example, here we see the Facebook network. To the left, we have the node-to-vec embedding, and to the right, we have the HTCN embedding. Observe that for the node-to-vec, bias is evenly distributed across the network, whereas for HTCN, some communities are embedded more unfairly than others. The user can then zoom in and inspect certain communities in more details, as well as get details on demand by hovering on a node. Now for the diagnostics view, the user selects a focal node from the interactive table to the left based on its unfairness score or its ID. The focal node is indicated with red, leveraging pop-out effect. Once the user selects the focal node, all the information relevant to its unfairness score are displayed in the two panels. To the right, we see the embedding subspace relevant to the unfairness score, and to the left, the corresponding graph topology. In this example, we examine the individual unfairness score, which measures for each individual node how close it is embedded to its neighbors. What do we see in this example? To the left, we have the two-hop neighborhood, where one-hop neighbors are colored in the darker color, and two-hop neighbors are lighter. And to the right, we have the 2D projection of the embeddings of these nodes. Is this node fairly embedded? Well, let's see. There is a community in the neighborhood that is closely embedded, except for the single node that is far away, which explains the computed unfairness. The two views are interactively linked, so selecting an area in one highlights the corresponding nodes in the other. Notice that before we used the concept of distance in the embedding space to define unfairness. It's clear that we need some sense of relative distance that involves the whole embedding space. For this reason, we also display the context, which is the whole embedding space, highlighting the area and the nodes we focus on. Here we get a sense of the relative distance by observing that the distant neighbor that we focused on earlier is far away indeed, since we're looking at a relatively large area. Finally, let's see how we support an individual and group fairness scores with an integrated design. For individual fairness, we care about the neighborhood of the focal node in the graph and the corresponding embedding. On the other hand, for group fairness, we care about the closest nodes in the embedding space and the corresponding subgraph. In both cases, the color encoding represents the properties that are relevant to the unfairness score computation. For individual fairness, that is the distance of a node from the focal node in the graph, whereas for the group fairness, it is the membership to a group. Think about gender or ethnicity information. To conclude, we designed Bioscope, a tool that supports a workflow for visual unfairness diagnosis in graph embeddings. The most important limitation we encountered is scalability, since real-world graphs are massive usually. We plan to investigate more sophisticated methods for graph abstraction in order to get an overview and overcome the computational limitations. We also plan to enrich our user options for embedding projections, for example, using HuMap instead of PCA, and our benchmark suite. Thank you everyone for your attention. Our code is available on GitHub, and we welcome any questions or feedback. Hello everyone, I'm Agapi, presenting our work, Bioscope, a tool for visual unfairness diagnosis in graph embeddings. This is joint work with Bruno Scarone, David Liu, Aditya Pandi, Brennan Klein, Tina Elias-Irad, and Michelle Borkin from Northeastern University. As machine learning systems affect more and more our lives, algorithmic fairness in this context has become an important topic for both researchers and practitioners. In our work, we focus on graph embeddings. That is a machine learning model that maps every node in a graph to a vector in a metric space. You see here a 2D projection of an embedding.
We're just gonna, okay, there we go. It looks like we have now stopped the video. Awesome, thank you. All right. Okay, so here's the question that has come in. So it seems like the current work is mostly on analyzing the outcomes of bias or unfairness scores. Do you have a method for visualization to explain the bias score in the graph?
Yeah, that's a great question. So essentially, our design displays all the information for one to understand how the unfairness score is computed. So in this sense, we are explaining there is some level of expertise that is required. So that's why we are targeting practitioners that work with embeddings, or even more researchers that want to evaluate their embeddings and understand the scores. But all the information to understand, to explain the scores, the unfairness that is computed is there. we don't focus on a particular task. That is, we don't focus on how the unfairness is manifested in a classification problem, for example, or a recommendation problem. We focus on the embedding itself and explaining the scores.
Thanks. We are unfortunately at time for this session and a few minutes over. So I want to take a moment to close things up. I'd like to thank all of our presenters today who did a great job. I'd like to thank folks both online and in the audience for bearing with us as we sorted out the technical challenges today, and thanks to the SVs for helping us kind of go through that. The papers are available online. I encourage you to reach out to the authors over the course of the week to continue the great conversations that we've started here today. So thank you again. For those of you in person, enjoy your break, and we'll see you in about a half an hour for the next session.